Today's lesson is going to cover topic 4.1 and 9.1. Because 9.1 is simple harmonic motion and 4.1 is oscillations, I think it makes sense to combine these two. Okay, so these are the IB physics guidebook descriptions for 4.1. I'm not going to read them to you. You can read them at your leisure. But it's important to note the last point under guidance, okay? You are expected to understand the significance of the negative sign in the relationship of acceleration is proportional to minus x, okay? There's not a lot of formulas in this unit, okay? It's a formula that we're already familiar with, and that's that the period is going to equal 1 over the frequency, so they're inverses of each other. Under topic 9.1, okay, we focus more on simple harmonic motion in particular and the energy changes, okay? Under 9.1, or the next set of PowerPoints, I'm going to go over the various graphs that we're going to see as well as the energy. Okay, this one has a lot of formulas. However, they're all pretty much related and we've seen some of them before. Okay, so there shouldn't be too much of a surprise. In particular, we saw the period equations last year, the period for a pendulum, the period for a mass spring, and we'll go over the rest of the equations in the next set of PowerPoints. Okay, this unit is kind of, has a lot of definitions, and I want to make sure that you know the definition. So I have a definition page. Okay, period and frequency we've already talked about. Period being the time required for one complete motion, frequency being the inverse of that. Okay, equilibrium is going to be the midpoint of a back and forth motion. Okay, for a pendulum it's straight up and down. For a mass spring system it's right in the middle. Okay, at the equilibrium point, okay, your forces should more or less, you should have effectively no sideways force. Okay, at the equilibrium. Amplitude is basically going to be the furthest distance from that equilibrium point. Oscillation is repetitive back and forth motions, and simple harmonic motion is a special type of oscillation. Okay, just to reiterate, that period and frequency are inverses of each other. I find it helpful to sometimes think of period as the amount of seconds it takes per cycle, one complete back and forth motion. And then frequency becomes cycles per second. However, cycle is not part of the unit. Okay, it's it just helps me to think of it, and if I'm doing dimensional analysis, it helps to cancel out certain aspects of the units. So under simple harmonic motion, okay, this is a special oscillation where the acceleration of the object is 1, it's proportional to the object's displacement from equilibrium. Okay, so if I think of acceleration and force, the farther I move it from the equilibrium point, the greater the force is, and it's linear. Okay, so it's a linear function of displacement. And the direction of that acceleration is towards the equilibrium. And that's where the minus sign comes in, okay? Mathematically, I would say that the acceleration vector is proportional to minus the displacement vector, okay? And the minus basically says if I displace it to the right, my acceleration is to the left. If I displace it to the downward direction, my acceleration is back to the, is upwards. Okay, and so that's what the minus sign indicates, okay? It's that the acceleration is the complete opposite direction to the displacement. Okay, so one of the most common simple harmonic motion systems that we'll look at is a mass attached to a spring. In this case, my system is horizontal, but it doesn't have to be horizontal. It could just as well be vertical. Everything applies to a horizontal or a vertical system, or any other angle as long as I can ignore friction. Okay, and the reason that this is the most common system is because Hooke's law says that the force is going to equal minus k, which is the spring constant, times the displacement. So this is a perfect example, okay? If I solve for acceleration, my acceleration becomes nothing more than minus k over m, where k is the spring constant, m is the mass, displacement. And so we see that simple harmonic motion formula perfectly in this situation. Okay, the pendulum is the other most common SHM system that we're going to look at, okay? Then the IB does require us to understand both the pendulum and the mass spring system. Okay, in this case, if I displace my mass just a little bit to the side, okay, then my acceleration becomes nothing more than g sine theta. Okay, I get that from analyzing the forces involved in this system. Okay, if I analyze the forces, okay, and rotate my axis, okay, to match acceleration, which is why we always rotated our axis. In that case, the only component that I have in the direction of acceleration is the force of gravity times the sine of theta. And dividing both sides by mass gives me acceleration equals g sine theta. And mathematically speaking, when theta is small in radians, okay, the sine of theta equals theta. It should probably have an approximation symbol in there. Okay, the sine of theta is approximately equal to theta, or because the sine of theta is opposite over adjacent, x divided by the length of my pendulum, L. Okay, so solving this again, I find that my acceleration is going to equal minus g over L times the displacement. But this again requires me to have a small theta. Okay, and so just looking at theta and the different signs, okay, notice how much of a difference I have when I'm just at 1 degree. Even at 10 degrees, okay, after I convert it to radians, my difference is only 0.1%. Okay, going up to 15 degrees, I'm off by about 0.3%. And so some people like to go all the way up to about 15 degrees. I prefer 10 degrees. But either way, just understand it must be a small angle. Once you go past 20 degrees, you're rounding up to 1%. And so 1% is 2 significant figures. Even 0.3%, if you recall, adjusted by 2 significant figures. So that's about as far as you really want to go. After that, it's like you're impacting your precision. So the position of the pendulum, or the position of the mass spring, we're going to be using sines and cosines. Okay, and this slide tells us how we derive that. Okay, because my acceleration is equal to some constant, the negative of that constant times delta x. My acceleration is also known as the second derivative of position. The first derivative being velocity, the second derivative being acceleration. And the only function I know whose second derivative basically equals itself is sine cosine functions. Okay, so if I assume that x of t has a format of a sine omega t, the first derivative becomes omega times a cosine omega t, and the second derivative becomes minus omega squared a sine omega t. Therefore, that constant or coefficient k equals omega squared. Okay, because the a sine omega t is x of t. Okay, so in terms of a phase shift, okay, why are sine and cosine basically the same function? If I don't know when they start, okay, then the phase shift, they look exactly the same. Okay, if I phase shift by pi over 8, okay, my two curves are just a little bit different. Okay, and if I increase that to pi over 2, my phase difference is exactly the sine wave and a cosine wave as shown here. Okay, if I increase my phase difference, okay, to a full pi, this is when I see something that looks like this, what we encountered last year, which is standing waves, and we will go and talk about standing waves again in the future. Okay, and it's important to realize that, oh, well, this is the phase difference is pi, or half a circle, 180 degrees. Okay, if I go past pi, then I'm basically repeating in the other direction. I don't know really which one came first. Okay, so a phase difference of greater than pi almost doesn't make sense. Okay, so the next two slides are basically going to show the derivation for the period of a mass spring system and a pendulum. So since my acceleration for a mass spring is minus k over m, my constant capital K, or that coefficient that I had a couple slides back, equals k over m, or basically my omega squared equals k over m. But remember, omega also is equal to 2 pi over the period t. So substituting, I find that my period squared is going to equal m over k times 2 pi squared. Taking a square root of both sides gives me the formula that I'm familiar with, okay? That the period of a mass spring system is only dependent upon the mass and the spring constant and multiplied by 2 pi. Okay. For a pendulum, follow the same formula, okay? Whatever is in front of the x is my omega squared. Okay, and then making the substitution for omega of 2 pi over t and solving for t, I find that the period of a pendulum is 2 pi square root of L over G. Okay, thank you.